Exercise 4.4, we're asked to check, is the intersection of a context-free language together with a regular language also context-free? And so the way we're going to do this is going to be a similar proof to the one in the slides or in the book about proving that the intersection of two regular languages is also regular by showing how to construct the product automaton, which is basically an automaton that simulates two other automatons at the same time and accepts if and only if they both accept. So let's see how we can do this formally. If I've got some push-down automaton described as a 7-tuple and some DFA described as a 5-tuple, how can I construct a new PDA that accepts if and only if both of these guys do? I basically simulate both machines at the same time. So I'm going to make a new machine. What are its states going to be? Well, it's going to be every possible combination of being in a state in P and being in a state in D. So it's going to be the Cartesian product of the states in P with the states in D. And what's the elements of the Cartesian product? Well, it's going to be all pairs of states where the first is from P and the second is from D. They share the same alphabet. I assume at the start that they did, and if they didn't, well, you replace sigma with like the alphabet that's a union of both alphabets. Otherwise, it doesn't really make sense to intersect these two languages. The stack symbols will still be the same, gamma, because this machine D is a DFA and will not be touching the stack. The transition function, we'll get to that in a moment. The starting state will just be the pair of starting states for both machines. The bottom stack symbol stays the same, and the final states will be the final states for both machines. So if you want to be accepted by both machines, you have to be in a final state of P and a final state from D at the same time. So it's going to be the Cartesian product of these two things. So now the tricky part is defining the action of the machine. So if I'm in some state, and again we're talking about pairs of states here, a state in P and a state in D, and I read a character from the input and I see some other character on the top of the stack, what am I going to do? Well, I'm going to transition to some other state, SP, SD, and push something onto the stack, gamma. And then what are these parts? Well, SP is going to be whatever state the PDA would put me in, right? So we ask the PDA transition function, if I'm in QP and I read A and I pop X off the stack, where do I go? And what's SD? Well, we ask the DFA what to do. So if I'm in state QD and I read the input A, it's just wherever I go to from there. So this new PDA is basically simulating the original PDA and the DFA at the same time. I know that the language that the PDA is going to accept is not going to be changed because no one else interacts with the stack, and the language that the DFA accepts is going to be the same, because the DFA only affects the second state in the pair, and the PDA only affects the first state in the pair. So what's the language of this new machine going to be? It'll be all strings such that this new machine P prime empties the input and lands in a final state. So, well, what are the final states of this machine? Well, the final states are going to be FP cross FD. Okay? And when do you land in a final state of this machine? Well, when you're in the language, right? And when do you land in a final state of D? Well, when you're in the language of D. And because you have to be in both final states of these machines at the same time, it means you need to be accepted by both of these machines, which means you need to be in both of these languages. So that tells us the language of this new construction is the language of P intersect the language of D, and the language of P was a context-free language, and the language of D was a regular language. Because these were arbitrarily chosen, that tells us that context-free languages are closed under the operation of intersecting with a regular language.